Hello everyone. In this video of linear algebra, we are going to talk about the inverse of a matrix and related topics. So when we are dealing with the scalars, we all have something called the reciprocal, right? So if I have a scalar C, I have also something called reciprocal of C. When we multiply them together, I will get 1, and it doesn't matter I do the product from which side, right? So that's what I have. 1 over C times C is equal to 1 whether from left or right side. So for matrices, we have something similar, and instead of reciprocal, since the matrix has so many entries, we are not going to invert them, and even if we do, when we multiply it by A, we are not going to get equivalent to 1 in matrices. If you remember, equivalent of 1 in matrices is the identity matrix. So what we need is something that when we multiply it from the left side or the right side by A, the result is the identity matrix, and that is what we call the inverse. So inverse is kind of equivalent to reciprocal for scalars, and the order doesn't matter. Now, clearly, because the order doesn't matter, it means that the matrix and the matrix inverse both have to be the same size, and they have to also be what? A square matrix. So what we do is we only for now define this inverse for square matrices n by n. Inverse is also n by n, and the product is going to be an identity matrix n by n. Okay? So the inverse we only define for square matrices. Now the question is, well, how do you calculate that, right? And there are different algorithms for calculating the inverse of a matrix. One of them that takes quite a bit of calculation is using what we call the adjugate matrix. An adjugate matrix comes from cofactors. So I think you remember from my previous lecture the notion of cofactors and minors, right? When we talked about the Laplace expansion, I showed you that the determinant, right? If you remember, the determinant of A was basically, let's say like A1, 1, negative 1 to the 1 plus 1 times determinant of submatrix M1, 1. Right, and so on and so forth. So this term, if you remember, we called it the minor, and when multiplied by that negative to the 1, negative 1 to the I plus j, we call it what? A cofactor, right? So the cofactor and the minor, we remember from the previous lecture. Now, if you form a matrix with these cofactors, we call it the cofactor matrix, and if you transpose it, we call it the adjugate matrix. So what do I mean by adjugate? Well, let me show you. So the adjugate of matrix A, if this is n by n, that is also n by n, and it is the transpose of the cofactor matrix. And cofactor matrix, let's say cofactor 1, 1 is what? It's negative 1 to the 1 plus 1 determinant of submatrix 1, 1. That's the first element, right? Then we have the second element, that is negative 1 to the 1 plus 2, that's element 1, 2, determinant of submatrix 1, 2, and so on and so forth, all the way to negative 1 to the 1 plus n, determinant of submatrix 1n, right? So then you go like negative 1 to the 2 plus 1, determinant of M2, 1, and keep going until here. And then you keep repeating, and this is going to be negative 1 to the n plus 1, determinant of submatrix n1. Keep going, negative 1 to the n plus n, determinant of submatrix n, correct? And so this is the matrix of cofactors. Each element in it is a cofactor. So this guy, we call it the cofactor matrix, and as I said, if we transpose this, the transpose is called what? The adjugate matrix. Now it says the inverse of A is this adjugate matrix divided by the determinant of A. So if I divide each and every one of the entries in this matrix by determinant of A, the result is going to be what? A inverse. Okay? So to show that in action for you, I'm going to apply it first to a simple 2 by 2 matrix. So if I have matrix A, B, C, and D, and I call this matrix A, first question is, what is the adjugate matrix? Well, it is going to be -1 to the 1 plus 1 times what? The determinant of a matrix that comes from eliminating first row and first column, so that is going to be times D. This is going to be -1 to the 1 plus 2, eliminating row 1 and column 2, so that's C. -1 to the 2 plus 1, eliminating second row, first column, so that's B. And finally, -1 to the 2 plus 2, eliminating second row, second column, so that's A. Okay, and then you transpose that, correct? So that is going to be what? That is going to be adjugate of A. Now, what is it going to be? So this is going to be transpose of what? So this is a 1, so you get D, -C, -B, A, and then transpose. So it is going to be A, D, A, -B, C, correct? Exchange the rows and the columns. Okay, D, -B, C, and A. And now what we need is to divide each and every element in this by determinant of A. But what was determinant of A? We had it in the previous lecture. We know that determinant of A was the product of diagonal elements minus the product of anti-diagonal. So it was AD, then minus anti-diagonal BC. So we have to divide each and every entry in it by AD over BC. So the result is going to be this. Okay? And as I said, you can apply that to each and every one of the entries. So if you want to write it as entry only, going to be D over AD minus BC, negative B over AD minus BC, then negative C over AD minus BC, and finally A over AD minus BC. So this is the inverse of a 2 by 2. Now, one of the ways that you can easily memorize the determinant, the inverse of a 2 by 2, or at least the adjugate of a 2 by 2, is this. The adjugate of a 2 by 2, if you compare it to the original one, right, this is A, this is adjugate of A. If you see, what happened is the diagonal elements are swapped. You see, D is up here, A is there. The anti-diagonal elements are not swapped, but in their own place they are negated. Right? So you see, the anti-diagonals are negated, the diagonals are swapped. That's the adjugate for a 2 by 2. And then, of course, divided by the determinant. Good? Now you might say, well, if I now multiply A by this, am I going to get an identity matrix? So let's do that. So A times A inverse is what? It is going to be A, B, C, D, and then times this guy here, correct? So let's copy it here and bring it up and multiply the 2 by 2 by 2 by 2, see what we get. So if we do so, going to be first row times first column, so it's going to be AD minus BC. And if you look, they all share the same denominator. Then first row second column, so it's going to be negative AB plus AB. Then second row, first column. So you're going to get CD minus CD. And finally, second row, second column, you're going to get negative CB plus AD. Right? And now if you look at it, clearly this is a 0, this is a 0, and then this is a 1, and this is a 1. So you will get the identity matrix 2 by 2. And if you reverse the order, I can again easily show you that the result is going to be the same. So I leave it to you to practice on it. So that's the inverse of a 2 by 2. But now if I have a 3 by 3, 4 by 4, and so on, so you can apply the same procedure. And it takes a little bit more calculations, but you can easily get the thing done. And in MATLAB, you can use the command inverse. So let's say if A is 4, 3, 1, let's say 9, 7, 8, 0, negative 1, and negative 6, right? All you need is to use the command inverse, and that will give you the result. And now if you call that inverse whatever you want, let's say A inv, correct? Now if you multiply A inv by A, the result is identity matrix, as you can see, 3 by 3. If you reverse the order and do it, again, the result is what? Identity matrix. And don't worry about these negative zeros, okay? So you clearly see it is doing its job. Now it is a computationally demanding operation because calculating the adjugate needs calculating n squared of determinants. And then you have to transpose it, and then you have to divide each and every one of them by determinant, and determinant also needs the same cofactors. The only good thing is the determinant and the A inverse, they all need cofactors. So once you calculate the cofactors for the determinant, you can also use at least a portion of what you need for adjugate will be calculated in determinant. The thing is, determinant only needs the adjugates for one row or one column, but A inverse needs adjugate for each and every one of the entries, so it is definitely more costly. Okay, and that's not the only algorithm in the literature for calculating inverse. There are other algorithms in the literature. One of them that is used, and that's quite fast, is called the Gauss-Jordan Elimination. We saw the Gauss-Jordan Elimination. So what you do here in this method, you will basically form an augmented matrix, right? And then you try to change it from AI to IA inverse. So what do I mean? So let's say here, for example, A is like 2, 4, 1, 6, 0, not 0, let's not use 0, 3, negative 1, negative 2, 1, and 5, right? So you want to invert that. So what you do, so this portion is your A matrix. You augment to it an identity matrix of the same size. Okay, so here, look, I add an identity matrix of the same size to my A. And then using elementary row operations, this is AI, as I said. I will convert it into I and something else. And that something else that you will see on the right hand side is going to be A inverse. Okay, so this is what we need to do. So here I will go ahead and first divide these guys by a 1, right? And to make life easier, let me avoid this 1 and make it, let's say, another 4. Okay, just trying to avoid decimals in the first place. So you will get a 2, 2, and a 1, but here you will get decimals regardless, because you have to divide the whole row 1 by 2, so you get a 0.5 here. And now you try to multiply an integer or any multiple of row 1 added to row 2 and 3 to get these two elements to 0. Clearly the numbers you need to multiply by is 6 over 1 negative of that, so negative 6, and negative 2 over 1 negative of that, which is positive 2, right? So here all I did is I divided the first row by 1/2, but now in the next step what I need is I need to say row 2 minus 6 times row 1, and then row 3 plus 2 times row 1. Okay, so I will get 1, 2, 2, 0.500. This is the top row. Now the second row is going to be 0. And then 6 times that minus this one, so you get a negative 9. 6 times that minus this one, negative 13. 2 times this plus this one, so that is 5. This is going to be 0. Then 2 times that, 4 plus 5 is 9, right? And now we need to do the same thing on the right hand side. So 2 times the first row added to the third row, so you'll get a 1, you'll get a 0, and you'll get a 1. And then 6 times the first row added to the second row, so you'll get a 0, you'll get a 1, and you'll get a 3, or negative 3 because you're subtracting. This is 1, but that is negative 3. So row 2 minus 6 times row 1, correct? So, and then row 3 plus 2 times row 1. Yes. Okay, so now I have to turn this into a positive 1 and then use it to eliminate this 5 and make it 0. So first thing, I multiply the second row by negative 1 over 9. If I do so, that will make that negative 9 a positive 1. Makes this 13 that I had. Change it to, let me make sure. So it was negative 13. You divide it by negative 1 over 9, you get positive 13 over 9. This one, that was a negative 3. It will be converted to a positive 3 over 9. And this one is going to be negative 1 over 9, correct? So this is what I have. Now I multiply 5 times second row and add it to the third row. So it is going to be row 3 minus 5 times row 2. Row 1 is not going to change. And row 2 is not going to change. And finally, if you look at row 3, you get a 0 and a 0. And then you multiply 5 times that, subtract from this. So that's 65 over 9. That is 81. So you get a 20. You get a 15. So you'll get a 15 over 9. Correct? And then what you need here is, again, 5 times that minus this one, so you'll get a negative 6 over 9, and then 5 over 9, and then 1. Okay, so I'm getting closer and closer to making it an identity matrix on the left. But here again, you see it's 15 over 9, so now I have to multiply this last row by 9 over 15 to make that element of 1. So if I do so, This element becomes a 1. This element has to be negative 6 over 15. And this element is going to be 5 over 15, or 1/3. Let's just write it as 5 over 15. This element is going to be 9 over 15. And that's it. So now I got it closer. Now I have to go back and first eliminate these two. Now here I'm going to go backwards. So I multiply row 3 by 13 over 9 and then by 2 subtracted from the first 2 rows to eliminate those two. And then I have to come and eliminate that 2, right? So if I want to do it, this is going to be row 3 is not going to change. It's going to be row 2 minus 13 over 9 row 1, and then row 3, not row 1, and then row 1 minus 2 times row 3, right? So if I do that, these guys are not going to change. This one stays, that goes to 0, this goes to 0, this is going to be 1, and this is going to be 2, and here you're going to have some calculations. Okay, it's not going to be as beautiful because now you have to multiply all of these numbers by 13 over 9, subtract from those, multiply by 2, subtract from these, and so on. So you get to this, and now finally you divide the first row by 1/2 to, or no, actually, you have to make it a 0. So what you need in the last step is you have row 1 minus 2, row 2 times row 2. And that is the ratio between these two numbers. That makes this guy a 0. So here you end up with an I3 by 3. And here you will end up with a bunch of numbers, and whatever bunch of numbers you get, that's A inverse. Okay, so that's what you can get an A inverse for. And here I can show you 2, 4, 4, 6, 3, 1. Correct? So A is 2, 4, 4. 6, 3, 1, and 6, 3, negative 1, and negative 2, 15. Negative 2, 15, and then what is inverse of A? Okay, so definitely getting to these numbers. I could do it, but since I was doing everything by hand, that's really what you will end up getting as A inverse, but the process is very, very clear, and you can, for example, also apply it to a 2 by 2, right? So I leave that up to you. So this is what you do, right? So this is your 2 by 2 matrix. What you need is to convert it into an identity on the left side. So first you divide by 1 over A. Right, that makes it 1b over a, 1 over a and 0, and then c d 0 1. Right, and then you multiply the first row by c subtracted from the second row. Let me do it actually. I changed my mind. I wanted to leave it to you, but you can do another one yourself. So 1b over a, 1 over a, 0. Here is going to be 0. Here is going to be d minus cb over a. Here is going to be negative c over a, and here is going to be 1. Yes? That's clear, right? What I'm doing, and now what I need is to make this guy a 1. And if you simplify this, that's dA minus BC divided by A. So that's the determinant divided by A. So what I need is to multiply that second row by A over determinant. That makes this guy a 1. Correct? So now you will get 1 B over A, 1 over A, 0, 0, 1, and then that is multiplied, so you get negative C over AD minus BC, and just A over AD minus BC. Good? So this is going to be so far. Now all I need is to eliminate this, and for that I need to basically add row 1 to the negative B over A times row 2, which is the ratio of these two numbers negated. If I do so, I'll get 1, 0, 0, 1, negative C over AD minus BC, A over AD minus BC, and now you have to multiply each element in here by B over A and add it to, subtract it from the first row. So if I multiply this by B over A, you get B over that, subtract, you get negative B over determinant. And over there you'll get 1 over A minus B over A times that. So it is going to be plus B C over A times AD minus BC. Okay, and all you need is to simplify this. Both terms have a 1 over A, so you can factor it out. It's going to be 1 plus BC over AD minus BC. And if you simplify this, you will get AD over AD minus BC. Then A and A simplifies, so the whole thing will be D over AD minus BC. And now if you look at the 1, 1 element, that's D over determinant, the 2, 2 is A over determinant, and then the diagonals are negative B and negative C. So you exactly will get what we talked about, right? This one. This whole thing divided by the determinant. And that is exactly the inverse of A as we talked about. Okay, so hopefully you learn how to do the Gauss-Jordan elimination and get inverse of A without calculating adjugate. Now you might say, well, that looks quite more complicated. Well, not really when you're doing it with the computer and the computer is just multiplying a row by something or adding it to another row. That's a lot easier than calculating all these cofactors. So in general, this method is faster than the adjugate matrix method. And there are other algorithms in the literature too. These two are not the only ones. Now, some important properties of the inverse. First is if you invert a matrix twice, you get the matrix back, kind of. Very, very similar to what we had in the scalars. If you do the reciprocal of the reciprocal, you'll get the number back. If you multiply a number times A and then invert it, it is like what? Inverting that number, taking reciprocal of that single number and then multiply it by inverse. If you apply a transpose to inverse, the order between transpose and inverse can be switched. So instead of doing inverse then transposing, you can do transpose then inverting. The result is not going to be any different. This is one of the most important ones. When you apply an inverse to what? To the product of two matrices, it is going to be applied to each and every one of the matrices, but the order is going to be reversed. Okay? So for example, if you have, let's say, 3 matrices multiplied like this, what's the inverse going to be? It's going to be C inverse, B inverse, A inverse. So you go backwards from right to left, invert and multiply. Okay, and finally, the determinant of inverse of a matrix is 1 over determinant of the actual matrix. So determinant of A inverse is 1 over determinant of A. Okay, these are some very, very important and useful properties of inverse. I'm not going to prove most of these, but just might give you 1 or 2 examples. But absolutely, we are not after proving each and every one. I leave it up to you. So let's say for the 2 by 2 matrix, if you remember, for the 2 by 2 matrix, the determinant of A was what? Was AD minus BC. Now, what was A inverse? If you remember, the A inverse was D negative B negative C and A divided by determinant. So now what's the determinant of this A inverse? Well, it is going to be, again, it's a 2 by 2 matrix. It's going to be the product of the diagonals minus the anti-diagonals. But remember, each and every entry in A inverse is divided by determinant A. So when you do that, it's going to be D over determinant times A over determinant minus negative C over determinant times negative B over determinant. Okay, and now if we do it, you see each and every one of them has a determinant of A. When you multiply, you will get determinant A squared. And here you will get AD minus BC, which by the way itself is determinant of A. So if you simplify, you will get 1 over determinant A. Right? So I easily showed you that for a 2 by 2, the determinant of A inverse is 1 over determinant of A. Good. And we can do any other thing that we want. We can work on each and every one of them. Now, one thing that might come to your mind is, what if I do addition or subtraction and invert it? Does it mean it is equal to A inverse plus or minus B inverse? Right? So can I apply the inverse over addition and subtraction? You see here, I applied it over a product, and it inverted each one but reversed the order. What about addition and subtraction, right? So here we can look at it with one single example. So A is, and we go with the 2 by 2 matrix, 2, 4, 1, and 5, and B is equal to, let's say, 3, 0, 6, and negative 7. So what is inverse of A plus B? This is this one. And then what is inverse of A plus inverse of B? That's this one. Clearly they are different. So the answer is absolutely not, right? You cannot apply the inverse to what? To the summation or subtraction, and it's not going to act like a distributive property. So the answer is absolutely not. Well, if you remember when we talked about transpose, do you remember this? Transpose, when we talked about it, I said, could you apply transpose to addition and subtraction? So what was this? If you remember, could I do such a thing? So can I apply the transpose to summation and subtraction? And if you remember, we use the command transpose in MATLAB, right? Or we can use a single quotation mark instead. So this is transpose of A plus B, and then transpose of A plus transpose of B is the same thing, okay? So the answer was yes, you can apply the transpose to the addition or subtraction, right? And here you can see them applied to the subtraction. The result is the same, but definitely not the inverse. Inverse is a way more complicated operation than swapping rows and columns. So this is right. And the transpose has something similar to inverse. When you apply to a product, it reverses the order of multiplication. But when it comes to inverse has the reversing property, but definitely you cannot apply to addition and subtraction. Okay, so please keep that in mind. Finally, we talked about all of this, inverse, properties of inverse, how to calculate inverse, but we had some limitation right in the beginning, and that was the matrix ought to be square. Now, what if the matrix is not a square? Can I still apply the notion of inverse? And the answer is yes. If A is a non-square, a rectangular matrix, then you still can apply something and get something called pseudo inverse, or more technical term is Moore-Penrose Pseudo Inverse. And it has two versions because the order of product does matter in matrices. Here you have two versions of pseudo inverse. One of them is called left pseudo inverse, one of them is called right. The left pseudo inverse is defined as A transpose A, the whole thing inverse A transpose. The right pseudo inverse is A transpose times A transpose inverse. Why do we call it that way? For this reason. The left one, if you multiply it from the left by A, right, so just plug in this whole thing up here, right, this is that pseudo inverse, this is A. If you look here, I have this matrix, whatever it is, A transpose A, and I have inverse of that. And of course, inverse of the matrix times itself is I. Now, can I apply inverse to this matrix? The answer is yes, because A transpose A is always a square matrix. A is m by n, and A transpose is what? N by m. So the result is going to be what? Whatever it is, if you call it B, it is going to be n by n. Okay, so since it's a square matrix, as long as it doesn't have a zero determinant, I can invert it. Good? But I have to multiply from the left side by A. If I multiply from the right side, I will get this, which is not equal to identity. On the other hand, the right pseudo inverse is what? When you multiply from the right side by A, okay, so you just plug this whole thing right here. Again, you'll get something similar. This time, your matrix of interest is A transpose, and multiplied by the inverse of it, again, it's going to be I. And the reason is A transpose is also square, because A is m by n, A transpose is n by m. So if you call the result of that C, C is going to be m by m. So first of all, A transpose and A transpose A, they are not the same thing. They have even different dimensions. They are the same thing if and only if the matrix is symmetric, okay, and a square. So, but in both cases, whether I, for each one of them, if I observe the direction of multiplication, if it's left, I multiply left. If it's right, multiply from right. The result is going to be I, which means that whatever this guy is that we define can be regarded as an inverse, right? Because when I multiplied by A, I got identity. So again, keep in mind, I have two pseudo inverse, and I show them with A plus, not A to the negative 1. And this is how they are defined. They are defined very similarly. If you look at them, they are actually very similar in the way they are defined, right? And so this is the way to go about defining an inverse for a rectangular matrix. It's called pseudo inverse or Moore-Penrose Pseudo Inverse, and you can calculate it. Okay, and I'll show you. But one thing that I need to emphasize is, I guess I mentioned it a few times, but let me emphasize it one more time for you, that if a matrix is a square, you cannot always invert it. Just because it's a square, it doesn't mean their inverse exists. If you see here, A inverse is an adjugate matrix divided by determinants. So because of this division, the inverse does exist when this determinant is what? Not equal to 0. So we say A is invertible, means you can find the inverse of it if and only if what? The determinant of it is not equal to 0, or if the determinant is not 0, we call it non-singular. If it's 0, we call it singular or non-reversible. You cannot find the inverse of it. So keep that in mind. Now the question is, what about the rectangular matrix? Well, first of all, rectangular matrix does not have a determinant. Okay? Does not have a determinant. Remember, determinant is only defined for square matrices, right? If you remember last time when we define it, you clearly see we define it for a square matrix. Good. Now you might say, well, this A transpose A that I'm inverting here, or A transpose that I'm inverting here, does it always have an inverse? Well, for example, A transpose A inverse, it exists if what? If the determinant of this matrix is what? Not equal to 0. Or the other one here, this other one, again, exists if the determinant of A transpose is not equal to 0. So the question is, now the fact that the product of these two matrices, the determinant of it is not equal to 0, what does it mean? Does it mean if I have any rectangular matrix with any types of entries, can I always invert this guy, or no? Under some conditions, the determinant of this matrix could be what? Could be 0, right? So what's the determinant of A transpose A when A is not square? Because if A is a square, right? So if A is a square, then the determinant of A transpose A, based on what we know from the determinant properties, is going to be the product of the determinants. And if you remember, the determinant does not change because of transposing, right? You have it here. So this is going to be determinant squared. So this is not 0 when the determinant of A is not 0, of course. But here the problem is A is not square, so I cannot separate it like this, and I cannot write it this way. Okay? The A transpose A, the whole thing is a square, but not each one of them, A or A transpose. So now the question is there any condition here on A, or entries of A, that allows me to invert this guy or not invert it, right? So if I have any square matrix, let's say, for example, a 3 by 2, right? So 3, 4, 1, and then 0, 6, 7, right? It's a 2 by 3, I'm sorry. Now, if I multiply A by A inverse, it's this matrix. Does it have a determinant? You see it does, and it's actually big. If I reverse it, it's a 3 by 3. Does it have a determinant? Yes. But look at the determinant. You see, it's almost 0, right? 7.69 times 10 to the negative 13 is almost 0. And when it's almost 0, it means what? It means this guy is not going to exist, right? So here, there are scenarios that A transpose or A transpose A could not, in general, be there. And I can investigate that, because by examples you cannot get a yes or no answer. But let's say if I make the case very simple by saying, well, let's say A is a 2 by 1, like A and B, or let's say C and D. And then what is A transpose? Well, it is going to be C and D. Correct? So what is A transpose? Clearly, this is a 2 by 1. This is a 1 by 2, so you'll get a 2 by 2. Right? So you will get basically C squared, CD, DC, and D squared. Now, what's the determinant of this here? Is going to be CD, the whole thing squared, minus CD times CD. Correct? Or C squared, D squared. We can write it this way as well. Minus CD times CD, and of course what? Guess what? The answer is 0. So if A is a 2 by 1, right? Definitely the determinant of A transpose is 0, regardless of what entries you use. Now what about A transpose A? Well, A transpose A is going to be a scalar, and that is going to be C squared plus D squared. So determinant of it is equal to itself. Can this guy be 0? Yes, when both of the numbers are 0. So you see, in general, we cannot expect that for a non-square matrix, these two terms have inverse in general. There might be some scenarios, arrangement of the entries, that this pseudo-inverse also does not exist. So it doesn't mean pseudo-inverse does always exist. So here I have this 3 by 2 matrix, and then I define a pseudo-inverse left to be equal to, or A plus left is equal to what? It was the inverse of A transpose times A, and then times A transpose, right? And this is the result. And now if I multiply it from left by A, you see I get an identity matrix, right? And then I can get the right pseudo-inverse for it. So the right pseudo-inverse is going to be something that when you multiply it from the right side, you will get the result, and that is inverse of A transpose. And remember, A has to appear here. So what you can do is do A transpose times that inverse. So when A here comes on the left and you multiply from the right side, you should be getting an identity. So that is A pseudo-inverse right. And now you say A times A pseudo-inverse right. And guess what? You don't get the identity matrix. Why is that? So you see, everything is good, right? We did it all right. Everything is good. We applied the definition exactly right? We did A transpose, inverse of A transpose. So nothing is wrong. But look at here, you don't get identity. Well, all you need is to scroll up a little bit. And you see something. It says, hey, your matrix was close to singular. What matrix? This matrix. You see, that's one of the cases I told you. That this matrix is what? Close to singular. So when you invert it, don't expect nice thing to come out. And when you multiply A by a right pseudo-inverse, do not expect that identity. So anytime you are trying to calculate left or right, if you see this warning that this matrix you are trying to invert is close to singular, which means a very, very small determinant close to 0, then do not expect when you multiply from left or right to get an identity, okay? In this previous case, you see, we did not have any problem when we did the left pseudo-inverse and we got this, but definitely not the right one. Okay, so please just keep that in mind, that not always these guys exist. So that's the idea of pseudo inverse that you can apply to a rectangular matrix. I hope the video was useful to you, and I will see you in my next lecture. Thank you.